Recall that for an n by n matrix A, we say that the determinant of A minus lambda I equals 0 is the characteristic equation. This is going to be an equation with the unknown or the variable being lambda, and it's going to be a polynomial equation. And the solutions to that equation are the eigenvalues of this matrix A. So we showed all that in a previous video. And then once we have an eigenvalue, we can look for corresponding eigenvectors as solutions to the matrix equation A minus lambda I V equals 0. Specifically, we're looking for non-zero solutions to this as our eigenvectors. We are guaranteed to have a non-zero solution because we know that the determinant of A minus lambda I is 0, and therefore this homogeneous equation, A minus lambda I V, will have a non-zero solution. Again, something we've seen in a previous video. So on to eigenspaces. So the eigenvectors associated with an eigenvalue lambda are precisely the non-zero vectors in the null space of A minus lambda I. Again, really just restating this idea of a null space being the solutions to that specific homogeneous equation. We denote this space by E sub lambda, so the eigenspace, and it is a subspace. It's a subspace of Rn, if A is an n by n matrix. And again, it's the null space of A minus lambda I. And we call this the eigenspace associated with the eigenvalue lambda. So we're going to see several examples in this video of finding, given a matrix, finding eigenvalues and corresponding eigenvectors and exploring this concept of an eigenspace. One thing that's going to be important as we move forward in this chapter is the dimension of that eigenspace. So we're going to ultimately be looking for a basis for the eigenspace in order to count the vectors in that basis and therefore determine the dimension. But in this video, we're really going to be focused more on just kind of going through several examples. So let's get started with a 2x2 example here. We're going to be finding eigenvalues, eigenvectors, and eigenspaces of this matrix. So to begin with, we're going to be trying to solve that determinant of A minus lambda I equals 0, right? So the determinant of A minus lambda I, so that's going to be the determinant of -2 minus lambda, 6, -2, 5 minus lambda. And this is a 2x2 determinant, so we can just use that AD minus BC. So that'll be -2 minus lambda times 5 minus lambda minus 6 times -2. So kind of expanding that, we would end up with a quadratic in lambda. So lambda squared, we'll get a -5 lambda. Do a few of the steps here. And a +2 lambda, and a -10, and then a +12. So this all becomes lambda squared, -3 lambda plus 2. So we are looking for solutions to lambda squared -3 lambda plus 2 equals 0. This is a quadratic. We could sort of always fall back on our quadratic formula if we needed to. This one, however, I think I can identify its roots or its factors here as lambda, what would this be? Lambda -2 times lambda -1, I think should work there. So we get lambda equals 2 and lambda equals 1 as our two eigenvalues. And let's just sort of put those somewhere for safekeeping because we're going to be referring back to them. Okay, and then let's kind of reset this page a little bit in order to kind of go to the next step of finding the eigenvectors and eigenspaces that correspond to each of these eigenvalues. So give ourselves a little bit of space. We're not going to need a lot of this. So next up, we're going to be for each of these eigenvalues looking at finding non-zero vectors in the null space of A minus lambda I for, again, each of these lambdas. So let's kind of go through them one by one here. We can start with, maybe we'll go in order chronologically here. So we'll start with lambda equals 1. And so we're going to be looking at solutions to a minus just I times v equals 0. So that's going to mean we're going to be looking for solutions. We're going to be subtracting 1 from this diagonal. So that'll be minus 3, 6, minus 2, 4, and then we'll augment that with the 0 vector. And so, what's going to always happen here is we're going to be able to, get a full row of zeros if we've done this right? So we know, for example, we could do a little bit of the row reduction. So not R3, we can do R1 divided by -3 and R2 divided by -2, just to sort of quickly identify that these are going to ultimately be the same, these two rows. So we'll get a 1, -2, 0, and a 1, -2, 0. And then we can do a row 2 minus a row 1. This becomes 1, -2, 0, 0, 0, 0. As you get the hang of this, you can probably sort of do a lot of this in your head, honestly, and sort of skip ahead just to that final result. But while we're building up, we'll go through each of the steps here. So what do we have? We have that if our eigenvector, maybe we'll just let v be a vector with the variables x and y while we're working in R2. So we have that, for example, y might be our free variable, and x is going to equal 2y. And so I guess E sub 1 here is going to be any vector xy such that x equals 2y. So we might write that that is equal to the span of vectors of the form, again, as long as x is 2 times y. So we might write y as 1, and then x would be 2 times that. So basically any scalar multiples of this vector to 1, and that's going to form our eigenspace. And any vector in this eigenspace would be considered an eigenvector. Let's go to now lambda equals 2, do the same thing. So we're going to subtract 2 from the diagonal of A. We're going to look at A minus 2i. So it would be a minus 4, 6, and a minus 2, 3. And again, we're going to augment that with the 0 vector. And so let's see here. Again, you'll notice that these two rows are multiples of each other. If you multiply the second row by 2, you get the first row. So we can reduce this, maybe rewrite it like this. So -2, 3, 0, and then just 0, 0, 0. We could put this into, sort of the reducer echelon form, which would introduce a fraction here. But, I think just we can kind of keep it a little bit cleaner here. What do we have? We have that -2x plus 3y has to equal 0. So as long as, I guess, 2x equals 3y, we've got eigenvectors corresponding to the eigenvalue of 2. So we might write E sub 2 is going to be the span of any vectors of this form. And so, for example, if we made x equal to 3 and y equal to 2, then, this would be satisfied. So we'll make x equal to 3 and y equal to 2. And this kind of keeps it a little bit cleaner without having to introduce fractions. If you had fractions, that would not be the end of the world, of course, but just to, again, sort of keep the values in our vectors here just all integers. So nice example here where we've got, each of these eigenvalues has a corresponding eigenspace, and each of those eigenspaces consists of the span of just a single vector. So, a single vector is going to span a space, and of course that set will just be linearly independent. So as we move forward, we're going to be thinking about bases for these eigenspaces. And so for each of these examples, the basis could just consist of that vector that we wrote. So the basis for E1 would just be the set consisting of the vector 2, 1. A basis for E2 could just be the set consisting of the vector 3, 2. And in particular, the dimension of each of these eigenspaces would just be 1, which is something that will not surprise us as we move through this chapter. But as we're starting these examples, something worth pointing out. Let's check out the next example here. So again, we're going to be looking for solutions to the determinant of a minus lambda I equals 0. So the determinant of -1 minus lambda, -1, 1, -3 minus lambda. So it'll be a -1 minus lambda, -3 minus lambda, and then a +1. So that will give us lambda squared +3 lambda plus lambda, so +4 lambda, and then a +3 plus 1, so that's a +4. And since I know I want to set this equal to 0 and solve it, maybe we'll just attempt to factor it. And can we do that? Yeah, I think this will just be lambda plus 2 times lambda plus 2, so lambda plus 2 squared. So if we set that equal to 0, we'll just get lambda equals -2. So just one eigenvalue here. So let's go ahead and look for the eigenvectors corresponding to this and the eigenspaces, or the eigenspace, I should say, corresponding to this eigenvalue. So we want to look at solutions to a minus lambda I equals 0, a minus lambda I times v equals 0, I should say. And so we're going to be adding 2, because subtracting a -2 will be adding 2 on the diagonal. So -1 plus 2 is a 1, and then a -1, and then a 1, and then -3 plus 2 will be another -1. And let's actually augment this, 0, 0. Okay. And then this reduces pretty quickly. We can see row 2 minus row 1. We just get a reducer echelon form. So we have, again, x, y. As long as x equals y, then we've got vectors in our eigenspace. So the eigenspace is going to be the span of, you could just say 1, 1 here. Okay. And so the dimension of the eigenspace here would just be 1, as we saw earlier. Same kind of idea. A single vector span will be linearly independent, and so the dimension will form a basis, and therefore we have the dimension as 1. This is a little bit more interesting, and again, the reason behind why this might be more interesting is something we'll explore a lot more later on. But this eigenvalue of 2, we would say, is a repeated eigenvalue, or -2, I should say, because of the factor of lambda plus 2 squared in our characteristic polynomial. And so, the fact that that was a repeated eigenvalue with multiplicity 2, and its eigenspace had dimension 1, is something of note. I'm not going to sort of go into more details than that, but that is something of note. Okay, another example of a 2 by 2 matrix. We're just, again, going through several examples in this video. So I should mention, as I'm doing these examples, it's probably worth you sort of pausing the video, and maybe I should have said this earlier, and hopefully you're kind of doing this, pausing the video, trying these out, and then, sort of watching my steps as I go. But let's go through another example. So determinant of a minus lambda I, again, will be the determinant of 1 minus lambda, -2, 1, and then -1 minus lambda. So 1 minus lambda, -1 minus lambda, plus 2. So that'll be a lambda squared. We'll get a plus lambda and a minus lambda. So actually that lambda term goes away, and then we'll get a -1 plus 2. So this becomes a +1. And so we're looking for solutions to lambda squared plus 1 equals 0. And so that would mean lambda squared would equal -1. Now, At this point, we might sort of go in a few different directions depending on what we're going to be doing in this course and sort of how we'd like to further go down with this path with eigenvalues and eigenvectors. Lambda squared equals -1 does not have any real solutions, and so that might be where we stop and just say, okay, no real eigenvalues. I'm happy here. It does have complex eigenvalues, so lambda would be, for example, plus or minus I, plus or minus the square root of -1. And there are certainly important problems we could tackle by exploring this idea of complex or imaginary eigenvalues. In this class and in this book, we're, at least for now, we could potentially explore this later, but for now, we're going to stick with just looking at cases of real eigenvalues. So we'll just stop here and just say no real eigenvalues. Okay, and just kind of say if you are in a position where you want to learn more about what situations complex eigenvalues could lead to, then I recommend checking out some other resources and some other videos. There's tons and tons of good information on that scenario.